All of physics is either impossible or trivial. It is impossible until you understand it, and then it becomes trivial.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind.
Your hosts here in North Devon, Matthew and George Russell.
Oh yeah, baby, Rutherford.
Ernest
Rutherford.
Sir Ernest Rutherford.
Sir Ernest Rutherford, the New Zealander. I'm not going to make that mistake again. He's a New Zealander, stroke British scientist, the father of nuclear physics. I'm joined on the podcast by George in a very last-minute substitute goalie fashion.
Yeah, all of the others cancelled. So
all the other
you were stuck with me.
We got lots of cancellations.
Yeah.
So it's a good episode today. It's about nuclear propulsion. I've got a great interview, George, with a guy called Paolo Venneri, who works for a company called USNC-Tech, who are building nuclear space stuff.
Nice.
So Paolo, got his PhD from Korea, but as you'll hear, he is very much a nuclear thermal propulsion kind of. It's in his blood. It's in his blood ever since.
I hope not, because that would.
I hope it's not actually in his blood. Apparently it's not that good for you.
Yeah, having radiation and stuff. It's just
People from Cornwall, they've got radiation in their
that
blood.
is true.
And I'm not just saying that because we're in Devon right now, and obviously there's a bitter rivalry. If you think the rivalry between France and England is big,
Yeah,
Devon and Cornwall,
the infighting is worse.
It's worse. So yes, Paolo is going to be the guest. I'm going to play that in a bit, but I thought we'd have just a quick rundown. It's only going to be a brief top and tail this week. I thought we'd have a quick brief rundown on some interesting points about nuclear power and space. Here's a question for you, George. Do you know about enrichment of uranium?
I mean, I don't know the exact things about the process, but essentially it's like taking uranium ore and then making it pure, uranium-235.
Yeah, so the more uranium-235. So uranium-235 is an isotope of uranium.
Yeah.
With a specific number of neutrons and protons adding up to 235. And the more you have of it, the more likely it is to go critical and create a terrible mess.
Or a good mess.
Like
if nuclear propulsion.
Like in nuclear propulsion or nuclear power. So, yes, highly enriched uranium is anything over 20%. Essentially, that means that it starts to become dangerous in terms of, it could be weaponized, but most weapons are 85%.
If 20% is sufficient, what do they call 85%?
Very sufficient. I think the bigger the percentage of uranium-235, the less mass you need to go critical. Right. So as it gets less and less and less, you need far more of it. Which
so it ends up being the same.
There must be a sort of certain amount of it that you need for it to go critical.
Yeah.
That I don't know, but the interesting fact that I did see was that you can actually go critical with only 5.4% 235 uranium. However, you would need infinite mass.
So if I have a 5.3999, I should be fine.
Yeah, it's impossible. No matter even if you turn the universe into uranium, as long as it wasn't enriched past 5.3, we'd be okay.
Okay.
Yeah, but why are we talking about nuclear and space?
Because nuclear propulsion, obviously.
Well, nuclear propulsion is definitely one of them, and I think we'll concentrate on that before we listen to my interview with Paolo. But I think it's becoming more and more of a thing because NASA released a report a few months ago. I think it was back in February, and we did report it on the podcast at the time. But they pointed out in that if you want to go to Mars using chemical rockets, you'd need at least 10 or 11 SLS launches just to carry the fuel for the mission.
So to put the fuel in orbit to go to Mars.
Yeah, to go to Mars.
That's insane.
Well, exactly. Well, considering
Never going to be done with an SLS.
Well, no, considering they're only thinking about one SLS a year, it would take a decade
just to get the fuel.
Just to get the fuel.
Just so you're in low Earth orbit.
Yeah.
And the Saturn V got in low Earth orbit in like a few hours, so or even less than like a few minutes. So that just goes, draws the comparison between Mars and Moon missions.
Yeah. Going to Mars is going to require a lot of fuel.
Yeah.
And the worst thing about chemical propulsion is it takes ages to get there as well, like 7 or 8 months. Whereas you can cut that time down using nuclear propulsion.
Yeah, well, the specific impulse of nuclear propulsion is literally almost doubled from like standard chemical rockets. Which
over doubles.
Doesn't mean just because it's like double the specific impulse, that's like over double, like way over double the actual efficiency of the rocket, because then you have less fuel, which means you need less thrust and it can go further. So you actually end up getting like 4 times or 8 times.
Now that is interesting. Yeah, that's
the delta V.
Yeah. So the delta V increases massively. So you don't have to take as much fuel with nuclear propulsion, but you could probably just do it in one nuclear propulsion rocket. Plus, you get there quicker, and getting there quicker makes it safer, as we'll hear in the interview. But it's clear that the nuclear propulsion is potentially insanely important for a trip to Mars. Now
you've got essential as well.
Yeah, I mean, when you get there, nuclear power probably on Mars's surface is probably going to be essential.
It's further away from the sun, which means solar panels are even, like they're no longer as good as they are on Earth.
So it looks like you'll need both nuclear propulsion and nuclear power when you get to Mars.
And of course, wind power is also off the table as well, because like there's barely any air on Mars.
Yeah, I don't know. I must admit, I haven't seen any artist impressions with wind turbines on.
And
Mars.
Also, the problem with solar panels is of the dust. They completely get covered up, which is why the last 2 rovers have both used nuclear.
Yeah, so that's
power.
That's a third type of nuclear power, which is just
RTGs, which is what they use on the moon as well.
Yeah, and all of these, Paolo talks about. So yeah, it's interesting. So you've got nuclear thermal propulsion and you've got nuclear electric propulsion as well. So so nuclear thermal propulsion, Paolo does a pretty good job of explaining what that is. Nuclear electric propulsion, however, is using things like ion thrusters and Hall thrusters.
Yeah, so it's the same as an ion engine, but instead of using battery and solar
powers,
you just use nuclear, and it's essentially an ion engine, but you're just using nuclear power.
Yeah, well, you'll have to have lots of ion engines because you want to use all that.
Yeah, even though they have the highest specific impulse of any engine, but the lowest thrust.
Yeah, terrible thrust. It's barely the weight of a moth on your hand is the thrust. It's something ridiculous.
It's only used to be turned on like 24/7.
Yeah. In other words,
barely,
when you're zipping around in the vacuum of space, you can get quite a lot of acceleration out of minimal thrust.
You just have to do it for a long time.
But taking off from the Earth's surface,
impossible.
Although
I did see a Kerbal Space Program run in which somebody managed to get into low Earth or Mars, even like the analog of Mars, just using electric power and ion engines.
Nice.
So it is possible, but it's just you have to be in the Kerbal Space Program universe.
So it's not possible on Earth. Only on what do they call Earth in
Kerbin.
Kerbin. Okay, right. So NTP's nuclear thermal propulsion, actually NASA reckon, is more likely than the nuclear electric propulsion option, because the nuclear electric propulsion option there's so much scaling up of all the systems, and the thermal management as well is going to be absolutely enormously difficult.
Yeah, I mean, just imagine like thousands of ion engines on a spacecraft. It's just going to waste so much on just engines alone.
Well, and I think it's the fact that if you've got this reactor as well, the reactor itself can only get rid of a certain amount of energy to the ion engines, and then the rest has to be radiated off as heat.
Yeah.
So it's like it's that makes it really complicated. The problems with nuclear thermal propulsion, though, is how hot everything gets, and making things resilient enough, but also the long-term storage of the hydrogen, and the fact that you've got to get the thing up to operational temperatures very, very quickly to sort of act as a proper rocket. So that's hard. But as we'll hear, the amazing thing is that the Americans got quite a long way with this particular.
I was watching
design.
an old documentary made in the 60s. And yeah, it's like amazing how far they got with the technology. They were able to do a full thrust run for an hour with nuclear propulsion. So
yeah, I mean, again, it's not the only type of nuclear propulsion. There was Ulam and Stanislav Marcin Ulam, who is really famous because he invented the Monte Carlo method of computation for a start off. But he also was the person that came up with the whole idea of Project Orion. In other words, using nuclear bombs, where you just basically drop nuclear bombs behind you and you just ride the shockwave out across the solar system, which sounds ridiculous, but you know, they followed that principle.
Any explanation of a rocket is ridiculous.
Yeah.
You're putting a person on a firework.
An explosion, always, yeah. So it's like it's so sort of more recent versions of it, like I guess things like Daedalus and stuff like that, which works on a similar principle.
Yeah.
Has smaller pellets that you're sort of blowing up. So you know, that's not completely ridiculous. And Val Cleaver from the British Interplanetary Society wrote a lot about nuclear propulsion, nuclear rocket propulsion. But they concluded back in 1949 that nuclear rockets were essential for deep exploration, but not yet technically feasible. So the Americans were the first to kind of pick it up with the Nerva project, or Nuclear Engine for Rocket Vehicle Application. And that program ran from 58 to 73, but was actually started, as with everything, in 1955. What do you think? What do you think the original purpose of a nuclear thermal propulsion was for?
The moon landings?
No.
Mars landings?
No. What is everything? What is everything initially invented for?
War.
War. There we go. Yeah. So it was designed as the upper stage of a intercontinental ballistic.
ICBM.
Yeah, intercontinental ballistic missile. So, but as soon as Russia launched Sputnik, everyone went, "Uh-oh, we need to get our space act together." Right, so that's when they made NASA, and it was at the moment that NASA became a thing. The moment NASA was like, it's NASA now, they transferred Project Rover, which was the name of this program, over to NASA. And so it became Project Nerva, although Project Rover was part of Project Nerva. So that Project Rover was the actual sort of project for building the actual rocket itself, the actual engine itself. And one of the things that they looked at is putting Nerva as part of the Saturn V configuration.
Yeah, on the third stage instead of a...
They were going to replace the whole third stage with a Nerva third stage and see how it compared with some of the other designs.
Even after the moon landings, they were planning on going to Mars on a modified Saturn V, where the only difference was the third stage was a Nerva.
Yeah. Well, yeah, so I mean, it was looked into quite a lot, and the actual, I mean, NASA considered Nerva a highly successful program. In other words, it met all the design goals it was going for. In other words, it worked. The thing worked. They did lots of tests.
They've got working engines that they could put onto a rocket right now.
Yeah, so yeah, I mean, it almost came. It never actually flew, so it never got to flight tests. But here's some of the things that are. So it's quite a simple design, but which is essentially turbo pumping hydrogen through a nuclear reactor, and then the hydrogen gets insanely hot and then is ejected out the back.
Yeah. Or some of it's also redirected to a pump that then pumps more fuel and so on.
Yeah. So there's complicated things you've got to get over. You've got to control the reactor,
which is actually used by rods that are painted like half with sort of like an insulative material, and then the other half is a reflector, and so you can rotate them towards the core, the reflector side towards the core to heat it, and if you want to cool it down, these rods then rotate 180 degrees, and then the insulative sides actually stop the bouncing of fission material.
Yeah, so I don't think I think in Nerva it was more of a drum, wasn't it, that surrounded it? So it's like a controlled drum. So yeah, it's graphite or beryllium is one coating, and that is a neutron moderator. And then the other side is boron, which is a neutron poison. Apparently, and that's how they control these things with neutron poison, which basically slows the whole reaction down. And so you could control it by rotating the drums. And I think
the later versions of Nerva did use the rods.
Rods, yeah. So it's In fact, what was that version? But anyway, yes. So the rods that
it did have a name as
but the rods had it may have even been Nerva 2.
No, I think it had like a weird name, like
well
Simon or something.
Oh, like Black Joe.
No, not Black. I don't know.
Because there's Uncle Tom, Uncle Tongue, Bloodhound, Sheesh.
I think it could have been. I think it was Sheesh.
Old Black Joe. So yeah, Old Black Joe was the sort of original design. But yeah, so you can control the reaction using these rotating drums. The other problem is storing hydrogen, because hydrogen's got to be stored at minus 253 degrees centigrade. Which is difficult. And then it gets heated to 2,500 Kelvin or 2,230 degrees centigrade, which is 10 times hotter than a pizza oven. And so that is, hard to build materials that A, can withstand the heat, but also can withstand the corrosion of hydrogen.
Also, hydrogen's really small as well, so it can slip through gaps of many material.
Yeah, so even if you've got the tiniest of leaks, you're in big trouble with hydrogen. Yeah,
hydrogen is essentially a proton.
But it's not even that. I mean, if you get it even cooler, it starts to become one of those quantum liquids as well. So it just like seeps through even something that's not a Bose
and Einstein condensate.
Yeah, or something like that. So
the fourth state of
I don't think you get it that cold though. But yes, I mean, hydrogen is tiny. It's the tiniest thing there is. It's smaller than flour or sand.
Really?
Yeah.
Even smaller than a sand.
It's even smaller than a sand. I know. It's hard to imagine that, but it is. And so you've got those problems. You've got the fuel. Plutonium can't reach the same temperatures as uranium. So for nuclear thermal rockets, they don't tend to use plutonium. Uranium-235 seems to be, or uranium-233. Slightly better because it's slightly lighter than uranium-235, but it's difficult to handle, obviously. So it's all a bit of a nightmare.
Although I was watching the tests, and there was very little health and safety in the 60s when it came to nuclear stuff. Like they're just standing around next to the reactor just before it's about to go.
Yeah, but I think the reactor, once it's got when it's got the rods in, is fine, isn't it?
The rods are rotated.
Yeah, it's fine. It's not radioactive. It's only when you actually set the thing going.
Yeah.
So 1959, they were looking at the Saturn V launch vehicle. This is where they were actually deciding what the Saturn V launch vehicle was going to look like, and
the paint job and stuff.
So again, the paint, how they're going to be
the colour.
white. No, I think like defining what it should be, defining what the Saturn V should be, and one of the models of Saturn V, the bigger than the Saturn V, was going to be the Nova, like a muscular Saturn V, like a bigger Saturn V. And they looked at it and realized actually that a chemical nuclear Saturn V would be considerably cheaper than building the Nova in terms of how much payload you could get into space. So they actually issued this contract for a reactor in flight test to prove this vehicle out. So they started, designing that. And so, yes, it was going to be an S1C first stage, a dummy S2 middle stage filled with water, and then the Saturn nuclear Nerva stage, upper stage. But even though an S2 actual stage would be used in a real mission.
They wouldn't just fill it with water.
No, they wouldn't just fill it with water. I don't quite know why they had to do that for that particular test.
But
they never did, but they never actually did do the test, which is really annoying, because if they had done, the whole of space travel might be completely different, because it does seem like this is like a really...
Although it looks like the Saturn V could have done it anyway, just with chemical.
What?
The third's gone to the moon. I mean, the third.
So one of the things was until they did the lunar rendezvous maneuver, which is this wasn't defined at this
lunar rendezvous maneuver.
So as soon as they decided to do that, I believe that meant that they didn't need this Nerva tug anymore, and so that meant that they didn't have to include it in the Saturn development.
So think smart, not hard.
Exactly. They thought smart in this case. But at the time, NASA were planning trips to Mars by 1978, permanent lunar base by 1981, deep space probes to Jupiter and Saturn and places like that. And this was all based around Nerva technology, right? And when they were thinking about the space transportation system, in other words, what would become the space shuttle, the whole idea was to have Nerva rockets acting as space tugs for everything that the space shuttle would just deliver to low Earth orbit. That was part of it. So Nerva was part of the Space Transportation System, or STS. Not to be confused with SLS. However, in walks President Nixon, and this is kind of like the beginning of the end, really, for the Nerva project.
Tory cuts.
It was a bit like Tory cuts, but basically, yes. I mean, to be fair to Nixon, the American public had grown weary of spaceflight. It's like the first few moon landings, it's ace, and then eventually everyone stopped watching it on telly after a while, like it's not amazing. But it's only the first that counts.
It's only a man landing on the moon. I mean, it's not that exciting.
Well, I guess once it's the fifth or sixth time, it's not. I mean, Apollo 13 was exciting because they almost all died. And I think Apollo 13 kind of was a wake-up call to everyone going, yeah, if we keep doing this, eventually we will have a deadly accident. So Nixon's not keen on that because it would affect his re-election. So he pushed things like the Apollo 17 launch around so that it didn't affect his election and all those kind of things. And so to try and keep Nerva going, they actually planned, a Nerva that would fit into the space shuttle loading bay and stuff. But eventually Nixon went, nah, enough's enough. And so on the 5th of January 1973, NASA announced that Nerva was terminated, and everyone was actually stunned, like totally annoyed.
Yeah.
Because it was like, well, hang on.
That is annoying. Like, it's a technology that could have got us to Mars.
Yeah. But not only that, it's 17 years of development in.
Yeah.
$1.4 billion had been spent on it, and the project was going really, really well.
Well, just for his own re-election, he ended it.
Well, to save money, essentially, the undoubtedly NASA was soaking up too much budget at that point, and it's like, well, what can we slash? And Nerva
can't give up on the military after all.
No, yeah, but you would have thought that Nerva was
they could have used that to bomb people.
Yeah, exactly. So yeah, it's interesting. Now, what is interesting, it comes up a little bit in the interview, is that do you know ESA have only ever used nuclear materials when they're doing collaborative launches with NASA.
I didn't know that. No.
So they've only ever launched. So nuclear materials has only ever launched on a American rocket, and I think there's a
Why
little
is
bit.
that? Are they just anti-nuclear or?
It's not they're anti-nuclear. I think that they don't. I think it's a sort of health and safety thing. Now, this is what I was trying to. Julio was trying to help me get to the bottom of this, but we didn't quite get to the bottom of it. So I'm going to try and find out what the actual ESA policy is. But I do know that the French and the UK are quite pro, and the Germans are quite negative about nuclear, particularly now.
Yeah, after what happened during World War II.
It wasn't anything to do with World War II. No, I don't know what it is. I don't know. But yeah, but the French are very pro-nuclear, and the British obviously are pro-nuclear. But no, the Germans definitely shouldn't get those two confused.
What about the Russians though? I mean, didn't the Russians also develop a nuclear
they did,
system?
but they don't think they got as far as Nerva. Be interesting.
And
to
they're
see
also currently developing a nuclear jet propulsion, which uses air instead of hydrogen.
Yeah, that's funny because that comes up in the interview as well. They're like a nuclear scramjet.
Because once you're on Mars, you can use that to land. Like a nuclear scramjet or nuclear just regular jet.
Nice. Okay. So yeah, I mean, yeah.
And you don't need fuel then. You just need the Martian air, which will be highly pressurized from coming into landing.
Oh, okay. Yeah. So could you use it to slow down, or does it have to go in in the same direction as your travel?
Well, you can just redirect it,
Oh, yeah.
around a tube or whatever.
Round a tube.
Yeah, tube pointing down.
That sounds easy, right?
Well, it's landing on Mars, Dad. It's not going to sound easy.
Well, yeah. Easy. Well, the upshot of ESA, by the way, not using nuclear power for a lot of their spacecraft. For example, New Horizons, when it went out to Pluto, obviously has to have nuclear power because it's too far away from the sun. Rosetta is one of the furthest you can get out while still using solar panels, and they were 14 meters long each. The solar panels. 64 square meters total surface area. That's how big you have to have solar panels to do stuff out in the sort of slightly distant solar system. So basically, if you want to go and explore and do proper stuff out in space, you need nuclear. There's an interesting one.
Yeah, because Elon Musk was showing the ITS, and he showed an image of it with solar panels out next to Jupiter. But at that distance from the sun, if you were able to produce energy for your crew at Earth orbit with the same solar panels, you're only barely able to power a toaster.
A toaster sounds good. I mean, that sounds
optimistically, of course.
Oh yeah. But I mean, a toaster is, I'd be chuffed with that.
Yeah, it's just that when you're past Mars,
I reckon, yes, you might be able to charge your mobile phone off it.
Yeah,
like a 12-hour job, like one of those really annoying solar panels that you buy for your caravan.
All you have to do is give up on life support.
Main
systems.
Basically, just give up all your main systems when anyone wants some toast. Everyone has to get into their space.
Hold your breath.
Everyone has to get into a spacesuit when anyone wants toast. So there's an interesting one that Julio sent over about Robert Zubrin's nuclear saltwater rocket. Now, I've not looked into that, but that looks really interesting. Anyway, George, would you like to hear the interview with Paolo Venneri?
Of course.
Okay, here it is. A cootie!
The Interplanetary podcast, putting the ace back into space.
I'm joined on the podcast by Dr. Paolo Venneri from USNC-Tech. Welcome to the podcast. I hope I got your name right.
You got it pretty good. Good accent on the Paolo.
We're here to talk about space, nuclear power and propulsion. There's probably no better person to ask to take us right from the beginning. What exactly is space, nuclear power and propulsion? Take us as though we're simpletons right from the beginning.
Oh, wow. All right. That's it's always the simple questions that it's like, wait, okay, that's actually a much longer answer. So at its essence, nuclear technology, kind of like one step higher. It's the science and engineering of harnessing the energy of the atom, right? Back in the early 1900s, they discovered that there's a whole bunch of energy inside of the atom. You just have to find a way to access it. The way that we're able to do that most effectively today is by splitting the atom. If you have a heavy enough atom, typically uranium-235, you split it, you're also able to release enormous amounts of energy. And this was something that was discovered in the early 1900s, and since then has developed into a mature and sophisticated industry throughout the world. The prime examples being nuclear power plants, providing clean sources of energies in a safe way that really enables a lot of human activities around the world. Now, one of the reasons why it's important on the ground is because it allows us to have large quantities of energies produced, without greenhouse emissions in a clean way. Now, when you talk about applying this to space, it's a similar concept. It allows you to create and bring with you energy anywhere. You just have to go with, a small amount of uranium, and then you're able to have, kilowatts, megawatts, even gigawatts if you keep scaling it up of power throughout the solar system. And this translates into capabilities to have, a power plant on the moon, in space, on Mars, providing energy, heat to power human activities in all these distant locations, as well as propulsion. Energy can be used for both doing things such as producing electricity, processing resources, processing atmosphere, living, as well as providing energy for propulsion. And now when we talk about how nuclear technology is used specifically in space, there's typically three ways that we look at it. The first one, and one that we're actually has been used since like the 60s, is radioisotope power systems. The famous ones here are radioisotope thermal generators. They were used on the Voyager spacecraft missions, on the Curiosity rovers. These are low power, milliwatts and watt scale power systems. They like to have long, consistent power levels, 50, 60 years, but small amounts. They're good for science missions. And this is taking the energy of isotopic decay of these elements, and they produce some small amounts of energy. Now, the next type is fission power systems. So this is taking that high energy concentration from the fission of an atom and converting that into electricity and heat. And the applications for this are very similar to what we have on the ground in terrestrial nuclear power plants. You make a small, compact nuclear power system, you deploy it on the lunar surface, and then you have a plug at the end of it where you can plug in all of your lunar applications, whether it's a moon buggy or an in situ resource utilization plant, power human habitat, you name it. The next type is what we call nuclear thermal propulsion. Nuclear thermal propulsion is it's an exciting application of nuclear power that has also been around since the 1960s. There was a concept that originally came out of Los Alamos National Laboratory as they're trying to reinvent themselves after the Manhattan Project, of finding a new application for nuclear power. And it's actually quite similar to a chemical rocket engine. With a chemical rocket engine, you have a chemical reaction that produces heat, heats up a gas that then gets accelerated through a nozzle to create thrust. With nuclear thermal propulsion, you just replace that chemical reaction with a nuclear reactor, where you have a nuclear reactor producing heat. You pass a gas through that nuclear reactor that then gets accelerated through the nozzle and then produces thrust. These are, at a very high level, the three applications of nuclear technology to space.
Let's take your last one. Let's take nuclear propulsion. They were obviously looking at that, like you said, back in the 60s and got quite a long way with it. Why was it abandoned, and why now does it look like something that we can pick the ball up again?
Well, so there's a couple really big differences between the 60s and now.
Haircuts is one.
But and these differences are both kind of technological, scientific, as well as cultural. I mean, from a technological standpoint, in the 60s, we were at the beginning of discovering a huge amount of things. From the computers we have today didn't exist then. our basic understanding of materials didn't exist then either. Like the material science has come forward an order of magnitude since the 1960s. And so they could come up with these concepts, but they didn't have the materials to actually make them a reality. So there was a large technical hurdle and materials development process that has happened since the 60s that really enables these from a technological standpoint, technical aspect. The other big reason why now it's happening, and I think is the reason why it didn't really happen back in the 60s and 70s, is that back then nuclear thermal propulsion was a purely government-focused program. It was funded and invested in by the U.S. government originally, in a certain sense, unfortunately, for military applications. And so once the military need was no longer there, the U.S. government had no reason to continue funding that type of application. Today, the approach that we as a company, as well as I think NASA is taking, is that anything that we develop has to have commercial implementation. And so one of the big differences that we have today in how we approach nuclear thermal propulsion is that we only use nuclear material that is actually accessible to commercial entities and can be used for peaceful purposes. If you're familiar with kind of like the materials that one can use to power nuclear reactors, you have weapons grade material, which is known as high enriched uranium. And then you have what is known as low enriched uranium, or LEU, which is non-weapons grade.
What is the difference? And presumably one is hard to make, luckily, but what technically is the difference, and why is it taken so long for us to have like commercially acceptable material like that?
So the difference between highly enriched uranium and low enriched uranium is the amount of uranium-235 that is present in the material. When we talk about elements, there are, to further complicate it, in addition to the element itself, there's isotopes. And isotopes have a different number of neutrons in there to kind of give it different nuclear properties. Uranium-235 is a specific isotope of uranium that fissions particularly easily. And so the more uranium-235 you have, the easier it is to create fission. The way nuclear weapon works is you try to pack in as much of this uranium-235 into a small volume as possible, and then to get a nuclear explosion. And so with a high density of uranium-235 or highly enriched uranium, you're able to make effective nuclear weapons. Low enriched uranium, which is the material that you use in nuclear power plants today, it's very difficult. In fact, it's actually, I think they argue that it's close to impossible to make a nuclear weapon with low enriched uranium. Now, never say impossible, because science and human ingenuity can do anything. But it becomes much more complicated and much more difficult to do that type of work with low enriched uranium. And so the reason why early on in pretty much any space application, you looked at high enriched uranium as the nuclear fuel is because it's much easier to make a small and compact space nuclear system with high enriched uranium. Back then in the 60s and 70s, getting anything into orbit was complicated, difficult, and hugely expensive. Today, we have SpaceX, we have all these launchers that are promising increasingly lower launch costs into orbit. So we can now take actually some mass penalties to get a system into space, and have the luxury of designing it around a fuel that uses a commercial grade and low enriched uranium system. Now, one of the key things that my team demonstrated 2-3 years ago is that you're actually able to design a nuclear thermal propulsion system that uses low enriched uranium that has similar, if not equivalent, performance levels to a highly enriched uranium system. And that actually caught the notice of NASA, where now their entire nuclear thermal propulsion program is based on the use of low enriched uranium, and which I think has given it a momentum that it hasn't seen since the 70s and 80s.
Yeah, I mean, it's really interesting because on the podcast, I've started noticing much more recently that there's a shift towards nuclear power, particularly when it comes to talking about journeys from Earth to Mars. And the UK government announced that they wanted to push it And NASA also announced that when they were looking at the feasibility of SLS flying to Mars, it would take ridiculous and enormous amounts of launches just to launch the fuel to get to Mars, and that nuclear propulsion looked like the obvious solution. So is this like are we seeing the perfect storm for companies like yourself to go, right, we are going to start developing these systems, and these systems are going to start getting developed rapidly?
I think we are getting close to that perfect storm. There's still a couple of things that need to move into place, but you can definitely see it forming.
Yeah, what are the few things that are standing in the way then?
The short answer that the momentum to have these, these enhanced capabilities in space needs to continue. I mean, historically, space agencies, they're at the whim of government funding, right? And priorities shift, as they rightly should, right? With every new governing body, every new political party, priorities within the government do shift. And this presents problem within an agency that has to have 10-year planning periods. It takes time to develop it and then deploy it, et cetera. And so continuity of these programs is actually a key thing to have in order to be able to develop them. The current nuclear propulsion program within NASA actually started under the Obama administration and had continued to support under the Trump administration. And then we're seeing now with the new Biden administration, continued support even well into that. So the fact that we're now, 3 administrations into this program, I think it's indicative that we're getting the momentum that you need to actually get these out. The other kind of key thing that is growing is actually the belief that it can happen. I mean, a NASA mission or a government mission, it'll get you 1 or 2 of these systems out. It's not going to ask for 20 or 30 of these. And so it'll always be a government system, government-owned, government-operated. The key to getting a sustainable, in-space infrastructure with advanced in-space propulsion is to have a commercial pull for it or a need for it by non-government entities. And if you have a government entity that has built the momentum to develop this technology and demonstrate it, we think there are current commercial applications that would definitely benefit from having this technology, and seeing it demonstrated will allow it to then be implemented into a commercial space, which is what we're going for.
In my mind, I've always thought that the launch of this type of material, that this nuclear material, is the tricky bit. Is that still the case? Is that still a defining factor about, obviously rockets do blow up no matter how safe a system is. They do blow up and scatter everything across large areas of land. So is that still a problem, the launching fissile material?
So I'm glad you brought that up, because that often comes up as one of the key issues brought to our attention about launching any nuclear system in space. So there's a couple of key differentiators that we have to talk about when talking about launching nuclear systems. There are radioisotope systems like plutonium-238, which have been launched safely for the past 60 years, which have a set of regulations applied to them. It's definitely heavily focused on preventing the spread of plutonium-238 with very good reason. When we talk about fissile systems, I don't know if you're aware, but uranium is everywhere. I mean, the ocean has huge amounts of uranium just sitting in it. When we talk about the launch of a nuclear system into space, we're actually able to design these systems so that if an accident, knock on wood happens, it would actually be able to come down and not have the impact that everybody is worried about. You would be able to come down, land in the ocean, and then sit there as a lump of uranium just sitting there. Because until you turn it on, it is only a lump of uranium. You could hold a rock of uranium and not worry about it. The key thing is to prevent what we call a criticality accident on reentry. And that's something that we have very straightforward engineering solutions for, whether it's you have the reactor itself break up into 2 large pieces, or you have what we call burnable poison wires that absorb neutrons and prevent any type of criticality.
It's a bit like the sort of next generation nuclear facilities that they're building that are essentially that are really safe just purely by their design in the first place?
Yes. It's something that if you keep in mind when you design the system, is straightforward to do.
There's obviously this public perception, isn't there? And annoyingly, particularly senators and stuff like that, often run by public perception, and they certainly do over in this country as well. How long do you think it would take for that public perception of nuclear bad, something else good? Because is that something that you feel that we have to overcome as well?
So if you had asked me this, 6 years ago, I would have said we have a long way to go. Today, when they were first launching, nuclear powered radioisotope systems missions into space, they would have protests outside. It would be very difficult to get things out, or it was difficult. But if I remember correctly, the last launch of a system with a radioisotope power system, it was barely a blip on the news beyond we're sending a space. Like the news was we're sending a car-sized rover to Mars. That was the news. And then and the news okay, by the way, it's got a nuclear battery on it. And I think that's showing that the trend is in the right direction. Like now we're talking about what is enabled, what we're doing. Cool, it's got a nuclear battery on it, but it's what it's enabling that is the news. And I think the fact that is now the trend of how things are going, it's indicative that we're already on that path where nuclear is becoming an accepted solution.
Does the nuclear propulsion element go hand in hand with the nuclear power element as well? The whole building power plants for use in space?
So they do go hand in hand in that there's a lot of common technologies. This is actually at its core one of the design architectures decision that we made at USNC, in that we have a common nuclear fuel technology that we apply across our different applications. Now, a nuclear thermal propulsion system operates in very different conditions. Turn it on for 20 minutes, operates at 3,000 degrees Kelvin, and you're sending hot hydrogen through the system. So it's different operating environment. Instead, the nuclear power system for space, it has to operate for 10 years. It has a different coolant. We typically look at other gas coolants, but not hydrogen. And the temperatures are only a mere 1,000 Kelvin, which is still pretty hot, but it's not 3,000 Kelvin.
Is the way that your company is set up, the USNC, it's set up to develop those technologies hand in hand, because that's the clearest path to develop the technology?
Yes.
Because there's terrestrial usage for it as well as space usage?
Oh yeah, yes, definitely. So the key thing here is that the core technology of USNC, which is our parent company, is the nuclear fuel, where you take what is known as TRISO particles. Think of it as little uranium kernels with multiple layers on them to keep all the fission products, all the bad stuff located inside. Then you take these little particles and then you put them inside of silicon carbide, which is what you make tank armor out of. That gives you an extremely safe, durable, accident-tolerant nuclear fuel. And so what we've done is we take that same technology that enables ultra-safe nuclear reactors on the ground, and we apply it to space systems. Because what makes a ultra-safe reactor on the ground is what makes a high-performance, again, ultra-safe reactor in space. And so what we do on the space side is we take that same basic technology and then we apply it to these higher power, higher performance systems. Taking that same infrastructure and then doing upgrades to it, particularly for nuclear thermal propulsion, but for the power systems for the lunar surface, it's actually the exact same fuel that we're using on the ground.
In the UK, I've seen this story come up a few times, is this terrestrial use of sort of more modular, smaller nuclear power plants. Is this the same sort of technology? And therefore, are we about to see an explosion, for want of a better word, of that kind of nuclear power plant spreading? Because it's a carbon neutral technology. The world really kind of needs that kind of localized power plant. why does it not get talked about more? And are we about to see this kind of proliferation of that sort of thing from companies like yourself?
I think we are seeing that. And you're seeing companies like Rolls-Royce talking about, further developing their space nuclear activities. You've got companies like, X Energy, BWXT, General Atomics, who for the longest time, since the 70s, they did cool stuff in the 70s, but it's been quiet since then. But now it's like, wait, we can take all that and try to bring it into space. So I think that is going to happen. A lot more of this transfer from terrestrial into space, but then vice versa as well. Because when we talk about developing a space nuclear system, particularly talk about the power systems for like the lunar surface, it's a perfect terrestrial system. It's the next generation terrestrial system because it has to be able to operate unattended, zero accidents and be able to handle all off nominal conditions guaranteed for 10 years. And that's what you want. That is the ideal for a terrestrial system.
Yeah, that's kind of my point. Is if I was a town planner, which thankfully I'm not, but if I was a town planner and I was just about to build an estate of say 10,000 new homes. And I was thinking we could have a localized power plant, and you've got the choice of things like geothermal and all those kind of things. Are these small nuclear power stations feasible for projects like that as well?
Yes. So actually, our parent company, the key thing that they're doing right now is developing and deploying terrestrial nuclear power plants. The first one being the micro-modular reactor, which is slated to be operational at the Chalk River site in Canada. I believe the target date is 2025. And there it's going to be the nuclear power plant sized at 15 megawatts thermal, ideal for remote locations where you need 15 megawatts thermal of power. When we talk about Northern Canada, everybody needs reliable power for all the way through the winter. And so those are many of the first use cases is having power in these very remote and difficult locations. Once you have it demonstrated and deployed there, it's just it's a few steps to having your small modular plants anywhere.
Yeah, I was going to say, there's probably nothing more remote than the moon or Mars, right? Apparently it's even more remote than Canada. or parts of Canada, probably probably not. But how did your part of the company start developing though? Obviously you've come along. How did you get into this, and how did the company develop?
So the backdrop here is that ultra-safe nuclear was a technology founded by my father back in 2011, Francesco Venneri. The founding principle behind USNC came about when my dad was asked, right around when Fukushima was happening, how can this be happening? This was a reactor that was designed by American companies, built by the Japanese, who have a track record of excellence in nuclear. How is this accident happening? And throughout most of the accident, my dad was saying, the Japanese know what they're doing. It won't get worse. And then it got worse. It's like, okay, all right, that was a mistake. It can't get worse. And then it got worse. That really kind of put him into thinking of what are the key problems in nuclear and how we approach it. And it came down to, the safety of a system, and a lot of nuclear systems are built onto them. You add additional safety systems to kind of build that safety into the system so that you're able to operate these large plants. And so the philosophy he took is, all right, what if we invert that problem and bring the safety down to that core fuel element? So if the fuel is safe, therefore the entire system is safe. That's the concept of ultra safe. And they were focused really on developing a technology that was safe, affordable, and easy enough to be accessible at a larger scale. And so that culminated in the design and then deployment of these micro-modular systems, which from a technology standpoint aren't exciting. They're not an R&D project. The exciting part is the fuel and that it can be built and be built easily. But that doesn't have a future beyond 10, 15, 20 years. And that's where we come in. Like the company is founded by visionaries. The vision is get this built, but we're always looking into the future of what comes next. And if you think about it, where is nuclear really enabling? That's space. Nuclear enables everything in space. And so back in 2016, as I was finishing my PhD at the Korea Advanced Institute of Science and Technology, KAIST, South Korea, not North, South Korea. We were doing a lot of that foundational work to show that you could develop these nuclear systems with or design them around low enriched uranium. And so based on a lot of work that I did there and a team of others, including Michael Eads, Vishal Patel, Wes Morrison, and a whole number of others, we started applying for these government grants through Ultrasafe Nuclear for development of technologies for nuclear thermal propulsion. At the time, much to our surprise, we were actually taken seriously, and they gave us a number of small business innovation and research grants that then turned into larger direct contracts with companies like Aerojet Rocketdyne, BWXT, and then eventually with the NASA program itself to further develop that technology. So we've gone from being 2 people back in 2016, 2017 to this month, I think we're hitting 36 people.
Was this enabled by a key insight that you had while doing your PhD?
My opinion is actually that using low enriched uranium in nuclear or in space nuclear systems has always been doable. It was just a matter of actually deciding to look at it and thinking that it was worth looking at. My background in my undergrad was I did a double major in physics and international relations. And a lot of the work that I did during the summers was working at Los Alamos National Laboratory, looking at non-proliferation technology. So looking at enrichment monitors that would go to enrichment plants, figuring out how to make sure that you have the correct enrichment coming out of these places, how to make sure that nuclear weapons material doesn't get out. And so when I looked at nuclear systems for space, I kept seeing HEU, and everything. And given my non-proliferation background, I was like, wait, there's no way that this is doable. Like there's no future to this. And when I looked around to see whether anybody had given it a serious look, I found that nobody actually had. Nobody had really gone and looked at whether you could build a nuclear propulsion system using low enriched uranium. And frankly, I think it was because either A, there was no need because the customer was always, the U.S. Department of Defense, which, HEU, cool, we'll do that. And then, I don't know, in a certain sense, laziness, because it takes more work to design a system that uses LE. You have to be more clever. You have to think outside the box.
You happen to have this sort of unique skill set going into your PhD then, that there's a kind of, it's almost like you had a bit of political skill as well in knowing about the proliferation and those other elements that you're never really going to have commercially viable systems. All the time you have a proliferation and a fuel material that requires armed guards, right?
Lots of armed guards.
Yeah. Well, an army. The nuclear propulsion system, for example, what point are you at in that kind of development of a workable system?
NASA has this great way of measuring the readiness of technologies, right? Yep. Technology readiness levels. It's great because it gives you a metric to talk about. It's problematic because with any scale, there's always problems with it. But as a system, I would say, nuclear thermal propulsion, particularly these ones that use hydrogen propellants, are on the TRL of like a 4-5. This means that many of these subsystems have been developed. They have been, some of them have been tested in relevant environments, but the system itself has never been brought together, not since the 60s or 70s. So that's where we are with like the nuclear system as a whole. The key, the key difficulties to resolve in a nuclear thermal propulsion system are the fuel and then the integration of the system. The fuel, because very few things, if anything, has ever operated at 3,000 Kelvin for extended periods of time and remained intact. In fact, back in the 60s in the U.S. Nerva rover program, as well as under the Russian test that they're doing at a similar time period, they would destroy their fuel. I mean, they would turn on, they would operate, but at the end of it, half the fuel would have went out the back, which is not something we want to have happen nowadays. And so a lot of work is happening right now in developing that nuclear fuel that is able to not only provide the heat and operate for those 20-minute burns, but do so in a way that actually it stays intact. That it's intact at the end of the test and at the end of the operation. This allows a couple things. One, it means that you're retaining all of those fission products. So you're not sending radioactive material out the back of the rocket. And two, it allows you to have a reusable rocket. I mean, reusability, we've always known it's a thing, but nowadays it's becoming definitely a required factor of anything you send into space. Every time you use it, it's cost saved, and it becomes an enabling system rather than a single slingshot.
With nuclear propulsion, what are the sort of key benefits over chemical propulsion? We've got highly developed chemical propulsion now. Why switch to nuclear? What's the advantage?
It comes down to the fact that there are no gas stations between here and Mars, or anywhere else for that matter. You have to take all your propellant with you, or if you're not taking it with you, you have to build a gas station at the other end. And so nuclear thermal propulsion has this unique characteristic that it provides high thrust, or it can provide high thrust and do it with a high specific impulse. Specific impulse is a metric by which you can measure the amount of thrust you're able to produce for a given mass of propellant. Higher specific impulse means you can go to places and do so with less propellant, and therefore bring more stuff, more payload, and be able to do more stuff at the end of it. Kind of like the car comparison, is with a chemical rocket. You've got a Ferrari. You can go accelerate really quickly, but you're not going very far because you got to fill up after an hour. With the nuclear thermal propulsion, instead, it's like a Prius. You're able to have similar acceleration to a gas-powered system, but you also have that fuel efficiency that you get from having a battery coupled with it. So you're able to go 10 times as far with the same gas tank.
What sort of level is that? Is it literally twice as far, 3 times as far, 4 times as far? What kind of difference does it make?
So in terms of specific impulse, the highest specific impulse for a chemical rocket engine is liquid oxygen and hydrogen, which you get something on the order of 400 to 500 seconds of specific impulse. With nuclear thermal rockets, you're able to go up to 900 seconds, which is two to three times as efficient with the propellant mass. And
that is purely down to the chemistry and the physics. You can't make it any better. You just can't get the chemical ones much better than they are already, and what the theoretical limits of your nuclear propulsion. Is there any other viable alternative, or is that essentially it?
I'm glad you asked, because there's actually a couple steps ahead past that you can go. With the 900 seconds specific impulse is what we call a solid core nuclear rocket. It's where your nuclear fuel is, in a solid form. You send a propellant, a gas through it, and that heats it up. This is the limit of that is about 900. Maybe you can tweak it up to 1,000 seconds, but that's tough. The next level from that is a concept it's called a gas core nuclear reactor. The limitation to your specific impulse is the temperature which you can heat it up. And so with the solid core reactor, your limit is 3,000 Kelvin. Solution to getting past that limit is, forget the solid aspect, just go to a gas. And then, then you can start getting to 2,000 seconds, this is a technology that is in the early stages of development. The tangential pathway to this was known as high power nuclear electric propulsion. With the electric propulsion, you're able to get thousands of seconds of specific impulse. Hall thrusters, you name it, the Vasimir engine, they're extremely high performance, but they have very low thrust, right? Because they're limited by the power you can get into them. Now, if you attach a megawatt scale nuclear power system to an electric propulsion system, now you're talking. Now you can get pretty appreciable amounts of thrust and very high specific impulse. The difficulty on that is that, to deploy a megawatt scale power system, we think will take a little bit longer than developing a nuclear thermal propulsion system. And so there's a longer development time.
Is that just the bulk of it? So to get a working power plant, it like the minimum size it can be is presumably quite big still.
Depends on what scales you're talking about. Like at a megawatt scale, the nuclear reactor itself is actually a small fraction of the total mass of the system. One of the interesting things about space is the only way to reject heat is to radiate it. And so when you're talking about with a nuclear power plant, your efficiency for your conversion of thermal to electrical, is 30-40%. And so if you want to have a megawatt of electric heat, you have to reject 2 to 3 times that amount of thermal energy. And so at that point, your radiators are becoming huge or pretty big. And so when we talk about a high-powered nuclear electric propulsion, not only are you developing the reactor itself, which arguably might be the easiest part of the system at that point, you also have to develop very large, high-temperature radiators. You also have to develop power conversion systems that can operate at 1,000 degrees Kelvin. You also have to operate electric propulsion systems to be able to work at that type of power. So instead of just being the reactor, now you have a couple other systems you have to develop. All doable. We think there's engineering solutions to all of it, but they are all development programs in themselves.
Yeah, but so the basic solid core propulsion systems, you don't have to worry about that because presumably it's chucking the heat out the back. Is that right? So you're not having to worry about it. See, that's why I've always wondered in my copies of JBIS and things like that, why every single nuclear powered spacecraft has got these enormous radiators. So that's it. It's literally you have to get rid of the heat.
You've seen The Martian, right?
Yeah.
So that spacecraft that goes back and forth between Earth and Mars, if you look at it, that is a nuclear-powered spacecraft because it's got an electric engine on the back and a reactor, and then those big radiators coming off of it. As a key example of that.
Right. Okay. In your opinion, do you think that when people do start going in rocket ships to Mars, that it will probably be nuclear propulsion and not chemical propulsion, or do you think that we'll probably be a mix of both, or what do you think?
I think it'll be a mix of both. Chemical rockets exist already. The heavy lift there is, getting to Mars and then producing propellant to come back on Mars, which is a big lift. But there's an engineering solution to it. With nuclear propulsion, you don't have to worry about producing your propellant there. The big lift there is to get a nuclear rocket into orbit and convince everybody that it's safe to operate. So they both have their difficulties, but I think both have an equal chance of doing it. And they both have their advantages.
I'm trying to see the advantages of chemical because, like you said, it's like the chemical rocket, the amount of fuel that you have to bring up just for a journey to Mars, and the fact that it takes so long, and you could actually get, shorter journey times, which makes the whole carrying fleshy human bodies just so much easier. For every halving of the journey time, presumably makes it orders of magnitude easier to do that journey.
It also makes it much safer. Space is dangerous. It's I think they call it the most hostile environment known to man, and with good reason. It's a vacuum. You have wild temperature swings from hot to cold. It's a very radioactive environment from solar flares, cosmic radiation. And so if you're able to minimize the time you have a human in space, in deep space, that significantly increases chances of success at the end of the day. And that's why NASA has been putting money and investment into nuclear thermal propulsion, specifically for those Mars missions.
With the technologies that you're developing, which one do you think we'll see first? Are we going to see nuclear power plants on the moon as part of that mission, or are we going to see nuclear propulsion start to be a thing first?
I was actually remiss in not pointing out that we also do radioisotope power. Nuclear thermal propulsion is largely plugged, like when it happens is when that first customer wants it, whether that's NASA or a government, that'll set the timeline for that. Similar goes for surface fission power on the moon. There's actually an increased chance that some private entity would be interested in having a nuclear reactor on the moon, and that'll set the timeline for that. Radioisotopes, radioisotope power, radioisotope heater units, those have an existing market, we think today, or an existing community that would benefit greatly from it. And at USNC, we actually have developed a new way of producing radioisotope power systems that makes them accessible to non-government entities. I mean, if you look at NASA programs or any national space program, they have used radioisotope power systems only for those most expensive big flagship missions that they have, because half their budget is going into that plutonium-238 power system. It's insanely expensive, but the capabilities that it gives you is huge. I mean, just look at these rovers that are on the lunar surface. That Voyager is still going and transmitting back. But it's a capability that, if you came at a lower price tag, would be enabling for a lot of things. You could go into permanently shadowed regions on the moon. You could survive the lunar night. You could even have applications down on Earth, exploration of the ocean. There's existing users potentials for it. And so what we're doing right now is we're actually demonstrating what we call chargeable atomic batteries, which take the concept of the radioisotope power system and replace the plutonium-238 with radioisotopes that are A, safer, B, much easier to produce, and therefore much, much more affordable. And so we think that actually that radioisotope power system that we're developing right now, the current target is to have one, have it demonstrated later this year, and then deployed in the next 2-3 years. We've actually already started engaging with the FAA to start the launch process for securing the launch approval process of these chargeable atomic batteries.
All those rovers that commercial companies are sending to the moon, all those, anything that anyone wants to do commercially, then suddenly they've got a choice between rubbishy solar panels that won't work on lunar night or these or nuclear batteries. It's the commercial equivalent of RPGs that the Voyager carries.
Exactly. And actually, even from a simpler sense, a rover on the lunar surface, the key enabling thing for them is to have a source of heat that allows them to survive through the night. And so we might not even produce a power system. We might just give them essentially a hot rock that they can put at the core of the rover, and then double the lifetime and science that they can do with a single mission.
Was this another case of people hadn't quite looked into the possibility that was something that you could do? Again, is that another case of exactly like the other cases you were talking about earlier?
The idea of using non-plutonium-238 radioisotopes, like we've known that you can produce heat with isotopes other than plutonium-238. It's just that plutonium-238 is a really good source of energy and heat. It has, 50-year half-life, so it can produce it for very long periods of time. Shielding requirements are very small, so you can have a very small, compact system. So the performance is really good. In fact, NASA, ESA, they should all keep using plutonium-238. It is enabling. If you're not NASA and you're not ESA, you don't need that. Like, simply being able to have heat for 3 months is already going to triple the amount of work that what you could do beforehand. And so taking in the perspective of, we just need something that is enabling good enough and is accessible to folks that don't have billion-dollar budgets. That's the perspective that we brought and are acting on.
Because obviously for some space agencies, even like the big space agencies, it could be a huge enabling technology then.
I definitely think so.
Yeah. Really, the company has is it 3 strands then? Is your part of the company, is it's all space related stuff, or?
That is our focus. I mean, our mandate is to develop the future.
Right. Okay.
And so space is where it is. I mean, we do dabble in terrestrial things. We've done some work on mobile reactors. there's interest in those. We've done some looking in some more advanced versions of the flagship terrestrial reactor, but our focus is space.
I'm going to go back to a point I made earlier on about public perceptions, because what's quite funny, we a few months ago we were talking to architects about buildings on Mars, and often they would use solar panels, and we would ask them, why are you using solar panels when Mars is pretty rubbishy for sunlight? Why aren't you using nuclear power? And instantly their response, and one of them was, almost shocking to me, was that the fact that we don't want to bring Earth's problems to Mars. And it's like, therefore there's a huge perception just instantly that nuclear is bad. How do you go about sort of demonstrating that these systems are safe, that they're not part of the problems that have been associated, rightly or wrongly actually, with nuclear power? Is that something that you think about at all?
Well, first of all, I object to nuclear power being called a sin of humanity. So that's,
I mean, same here, but I just know that particularly in Europe, there is a kind of feeling that there's an ideology against nuclear power. We had
my family is Italian, so we have all of my extended families in Italy.
Yeah.
We go back and forth a lot, so I'm quite familiar with nuclear complications.
Yeah.
I would actually kind of flip it on its head. I mean, nuclear power is the result of groundbreaking, civilization-changing discoveries on the structure of the universe. And it's the application of those discoveries to give us enabling amounts of energy. I mean, if without energy, we would still be, living in caves with, knocking rocks against each other. And so if we don't go to Mars with nuclear power and nuclear technology, we'll always limit ourselves to essentially being what I would think passive observers of the inner solar system. Sure, we can make these large, magnificent telescopes to look out, but we'll never be there to see firsthand what is happening and make those discoveries in person. We'll only be observers. And so, if we're content to be a civilization that is going to sit here on Earth and look out, sure, I mean, we can work with solar and do that. But I like to think that we want to be more than that. I mean, that whole the whole idea of exploration, of expanding human civilization, going and bringing humanity beyond the cradle of the Earth. That's going to happen because of nuclear power. If we bring it with us, and that's going to enable us to go there, not just to visit, but actually have a meaningful, permanent presence. That's what I would say. I mean, we can't do it without nuclear technology.
Yeah. Well, yeah, that's really well put. I mean, when you finished with nuclear fission technologies, are you going to start looking at nuclear fusion technologies, or is that not so useful in space?
No. So are you familiar with this? What's it called? Icarus?
Yeah.
Project Icarus?
Yeah.
From the British Planetary.
Yeah.
No,
yeah, it is.
British
Yeah, it's British Interplanetary Society. Yeah. And Daedalus.
So, yeah, Project Daedalus. That's right. It was Icarus. Now
well, Icarus is the later version of it. Yeah.
So, fusion, as always, has infinite promise and potential. My father went into nuclear engineering because of fusion. And this was in the 70s. 80s. Okay. He went into his PhD doing plasma physics because of fusion. Back then, fusion was only 10 years away.
Yeah.
It has been 10 years. Well, it has alternated between being 10 years and 20 years away for the past, 40, 50 years. My perspective is that if we want to do stuff today and have it done so that my children can see travel between here and the moon and Mars as a routine affair, we need fission power systems. And so that's why we focus on fission. fusion is something definitely is something that would be one of those next steps after we have already established that kind of routine transportation. I mean, if you want to go from here to Andromeda, you're going to need a fusion system. Daedalus and Icarus, they've got that right. But that's not enough. We want to do it today, not in 100 years.
It's fission for the solar system, fusion to get out.
I would say that's a fair characterization, yeah.
There's one thing that I didn't ask earlier on, which because I'd not really thought about this before, was the thrust that you get from nuclear fission engines. Is that actually enough? Is there enough thrust from that to be a launch vehicle?
Back when we first were doing this, I actually got my start at a research institute at Idaho National Lab called the Center for Space Nuclear Research.
Right.
This was and continues to be an amazing educational opportunity for students, whether they're undergrad or graduate students. They take students from all around the world. There are a bunch of British, Canadians, Australians, in addition to Americans. Wonderful place. And there, essentially, you were given research projects to look at. Among these, there was also, one of the projects was, what would a nuclear thermal rocket look like if you're trying to have a surface to space launch vehicle? The answer is, you can do it. I would not recommend it. I know nuclear thermal propulsion is very good as an in-space propulsion system. It allows you operate for 20 minutes at a time to get out of into a Mars intercept orbit. You operate at the other end to get into Mars insertion, slow down around Mars orbit, then similar deal to come back. There's a couple of difficulties about having a nuclear thermal propulsion system to be your surface to orbit propulsion system. The big one is that a nuclear rocket weighs a lot more than a chemical rocket engine. Like the chemical engine itself, it's pretty light. It's in the tens, maybe in the hundreds of kilograms. A nuclear thermal rocket, the lowest mass you're probably going to get is a metric ton. Like that, and that's the nuclear reactor itself. And when you're going from ground to orbit, you don't want to use a metric ton of payload for your rocket engine. Then there's operating a once passed through nuclear reactor in Earth's atmosphere, which is complicated.
So you can do it, but it's not recommended.
There are better options.
Yeah,
chemical rockets are very good.
Yeah, because I noticed right at the end of I don't know if you've seen the program For All Mankind, but right at the end they have a souped up space shuttle called Pathfinder it's launched on the back of a jumbo jet, but it has nuclear.
I have not. I'm still on episode 3 of season 2. You've giving it away from me.
Well, there's a massive spoiler. I've ruined it for not only the listeners. I've ruined it for you. You can. You should.
All right, I am definitely going to have to go and finish season 2.
Oh, the season 2. If you're on season 1, it's.
Well, I did finish season 1.
Oh, so you
finish season 1.
I think I'm
like episode 3 of season 2.
I think you're only about half an episode away from mentions of Pathfinder. I mean, it's only at the end. It's just a silly little detail. I'm thinking, is that right?
They have been mentioning it continuously. It's like, okay, this mysterious Generation 2 space shuttle. I was like, oh, okay.
Yeah. It won't ruin the plot. Actually, it's just right at the. It takes off the back of a jumbo jet with nuclear propulsion, and I'm thinking. I mean,
there are concepts like nuclear scramjets. Have you heard of these?
Yeah, go ahead. Yeah, how does a nuclear scramjet work?
These are. There's theories about what the Russians were testing in the Bering Sea a couple of years ago, right?
The avant-garde.
Flash.
Yeah.
Among the theories is that it's a nuclear ramjet, where you have a nuclear reactor with essentially a funnel on one end to take atmosphere in. They superheat inside the nuclear reactor, and then it goes out the other end to create thrust. I wouldn't recommend it. Very cool, but not recommendable.
Before we move on to more frivolous questions, is there anything else that I've missed?
One thing I would add is that nuclear is an international field, right? I mean, you have nuclear experts, centers of nuclear excellence throughout the world, by design. Where the whole concept of the Atoms for Peace, the International Atomic Energy Agency. You have centers in the UK, France, US, South Korea. It's a global technology. And I think like it's only reasonable that it be applied in such an enabling way to space. I mean, the peaceful uses of nuclear technology in space, I think, are, they're already enabling on the ground, but they're truly enabling in a paradigm shifting sense for space.
Will it have to involve some form of space manufacturing where because these things are big? Will the sort of better systems and the bigger systems actually work better once you've got that capability of actually building things in space rather than building everything on the ground and launching it in massive fairings?
So this is something, it's similar to like a domino effect. In order to do that big in-space manufacturing, you need a power source. The only way to get a power source up there that is small, compact enough and give you power density to do that work is nuclear. Once you have that in-space manufacturing capability, producing, enabled by that level of power that you're able to send up there with nuclear, it's almost a self-fulfilling prophecy at that point, that you'll be able to build bigger, more capable systems that take you farther, faster, and allow you to do more.
That's a really interesting point that I'd not really considered, is that the in-space manufacturing requires a power source, and it might just be that the power source that's required is just about launchable in nuclear form rather than any other form.
NASA has this initiative they call the Lunar Surface Innovation Consortium, where they're trying to bring industry, academia, and government folks together to talk about, what are the technologies, what are the developments, what is the architecture of being on the moon, what is it going to take? And this is actually a pretty international body of folks. And the ISRU group, or the In-Situ Resource Utilization group, it's one of my favorite to go in and check in on, because when they talk about the stuff that they want to do, they're not interested in anything less than like 100 kilowatts electric. And they're like, this is for a first, zero generation demonstration. What we really want is megawatts. Again, and that's when we can start doing more interesting things like producing propellant, producing iron from lunar regolith, melting, any type of process. You need large amounts of heat, electricity, heat, energy. That enables everything.
My actual background is in music production, and you can't even do a decent gig without tons of electricity. So
how much electricity do you need for a gig?
Lots. It's all big C-form connectors. It's getting better because the lighting is so much. LED lighting requires so much less than tungsten. But yeah.
Oh, tungsten bulbs. Yeah, that take it. That takes some power.
If you went to see some of the old rock bands, then just the lighting rig itself is just ridiculous in its power draw. But but
that's a lot of heat. You need air conditioning on top of that.
Oh yeah. It gets hot. But I totally sympathise. Electricity is everything, isn't it? When you're trying to do stuff, it's useful.
Yep.
Yeah, that is a really interesting point. That it's such an enabling technology that it kind of enables itself as well, doesn't it? It enables the little brother enables itself to go into a much larger family of units, presumably.
And that allows you to build an infrastructure, a sustainable and permanent infrastructure in space.
Yeah.
Right. And that's what we're going for.
Yeah. No, absolutely. It's really, it is actually genuinely exciting, because in some ways we've been stuck, haven't we, since the late 60s, early 70s. It's a little bit stuck, and there needs to be a technology that enables that next step. And there's a whole heap of them, like you said, SpaceX, and obviously developing some of those technologies. But yeah, clearly there's a space.
Getting into space is definitely a very important thing. Like reducing those launch costs, that has enabled a lot of our dreaming. Like being able to send something and not pay its weight in more than gold allows us to have realistic plans and expectations of what we can do in space. So I can't actually credit these reduced launch costs enough. into being that kind of like trigger point that allows us to build that next stage.
I'm going to get onto some frivolous questions.
Go ahead.
So if you were to bring back a superhero from the past to show them what you're up to now, what your company's all about and the technologies, who would you bring back? Who would you bring back to kind of go, I'll have a look at this? Who would be interested in what you're doing?
So now I'm curious, what do you mean by superhero?
Someone from the past that you've kind of looked up to or read about or thought, oh, they're really cool. I'll give you a clue. For me, I would definitely bring back Richard Feynman for anything. Because I know it'd just be cool to hang around with.
So the urban legend at this point as to the origins of nuclear thermal propulsion is that it was an idea thrown around at the cafeteria at Los Alamos during the Manhattan Project. And that the scientists who were talking about it back then were like, there's no way that anybody would ever think of doing this. This is totally nuts. I'm not even going to patent it. I'm just going to, whatever, throw it around. And then the person who came up with the concept is reputably Enrico Fermi. So if anything, I would bring Enrico Fermi and show him like, hey, we're actually doing this.
Oh yeah, do you know what? I did actually read that in Richard Feynman's book. He mentions that whole they're literally picking off patents because the government are going, what can we do with it? I think even Feynman had some kind of space application for nuclear as well as one of his patents. That's really cool. Yeah, Fermi's definitely one that deserves to be on the list.
Nice. Yeah, deserve to see that it actually did happen.
Yeah. I mean, super.
Knock on wood, it's happened.
Super cool. Anyway, what a guy. And my final question that we ask all our guests is we've got a space song playlist, and we always ask our guests if they have a space song that they associate with space and the work that they do. You're not allowed to have David Bowie or 2000 or Richard Strauss's 2001 Space Odyssey theme music.
I think I've got two, just in case one of them isn't allowed.
Oh no, you can have two. If you've got two, you can have two.
I'm assuming you've seen The Fifth Element.
Oh, I love The Fifth Element. Yeah, it's one of my favorite films. Yeah.
Okay, there's that one scene in the opera house.
Oh yes,
that song. I was listening to the other day, and it was like it's a quirky opera song, but the scene is what makes it a space song.
Yeah, no, absolutely. Do you know that's really weird because I was watching it the other day as well, and I hadn't thought about it for years, and I was watching it the other day. But it's called.
All I know is like it's the Blue Alien opera song.
Yeah, but it is called something like Impossible Opera or something like that. By Nerva.
I think so. Yeah, it has that like that interesting vocalization at the end, like hitting octaves nobody should be able to hit. And
the reason why I was watching it is because that some singers attempt it. So there are sort of YouTube videos of opera singers actually trying to do, and it's most impressive. It's going on the list. So that's an excellent choice.
The other one would be like the intro to Star Trek Voyager. The theme songs for Star Trek Voyager.
Oh, interesting. That's not on either. Yeah, that's going on as well.
Really?
Yeah.
Oh, come on. I think that's the best of the Star Treks.
Really? Well, you can't beat the original, surely.
Well, I don't know. Voyager has always had a soft spot for me.
Yeah. Yeah, I mean, it is good. It is. Don't get me wrong. It's not the original though. But I guess I'm a lot older than you, so I grew up with Captain Kirk. And where's the best place for people to find out the kind of work that you're up to?
So we have a website, USNC.com. To actually find the stuff that we're doing on the space side, there's a little tab at the top right-hand corner of the website that you toggle between Earth and space. And if you click on the space side, there's a cool animation that goes in and shows you all the space stuff that we're doing.
And what does USNC stand for again?
Ultra Safe Nuclear Corporation.
Right.
We get interesting reactions to the name, but at the essence of it, we really believe that any nuclear system has to be first and foremost safe. What better way to show it than have it, in your name?
I mean, you're kind of halfway answering one of my questions earlier on about how do you persuade the public that it's going to be okay. I mean, your name kind of does a lot of that for you, doesn't it?
I'm remiss to say that, like, probably one of the best ways to see what we're doing on a day-to-day basis. You can also follow us, or we have a LinkedIn. We're pretty easy to find, USNC-Tech on LinkedIn. We put a lot of updates on there. And then, if I remember correctly, we actually have a pretty active Twitter account that shows, day-to-day things.
So Paolo, apparently you've got a very interesting generational family story. Are you able to share it on the podcast?
This is actually fairly embarrassing. My first introduction to nuclear thermal propulsion, I don't know, I was like maybe 7 or 8. My dad worked at Los Alamos National Lab working on accelerators, fancy nuclear stuff. But he would work with a lot of folks that were around in the 60s and 70s working on nuclear thermal propulsion. And so he would come back home, and I don't even remember what the occasion was, but he talked about nuclear propulsion, and he would explain how some of his current coworkers used to go to the Nevada desert and test these nuclear rocket engines, light them, show that they worked. And in my 8, 9-year-old understanding of the world, I had this concept of a nuclear engine chained to the ground, pointed to the sky, and then lit. And that's how you would test them, right? You would then have this nuclear rocket trying to take off, but held onto the ground with these big chains. So very. Now that I've been doing this for a number of years, I understand that is not how you test engines. You typically point them down so the nozzle is pointing up, so you don't have to deal with the chains and things like that. But that image of a nuclear engine being tested in the middle of the desert was definitely a romanticization of nuclear engines that has kind of stuck with me throughout and God, kept that passion going.
I mean, it's just hugely in your blood, then, isn't it?
Yeah. You could definitely say that.
And what about the other side? You've got kids?
Yeah, I do have. I have a son who is going to be 5 months in 4 days.
Is he going to go into nuclear propulsion as well?
Well, okay. So I wouldn't want to make him do anything. I would be very happy if he did. I was actually talking about this with one of my coworkers here, Chris Morrison, and like the reason we do all of this is, yes, it's cool. Yes, it's awesome technology. Yes, the idea of space is attractive, but the reason we do this is so that for our kids, it becomes a routine thing to be able to go to the moon, to Mars, and travel the solar system. Like for us, it won't be routine for us. We're building this, but we want our kids to have this be a routine thing, so that, frankly, it shouldn't be a big deal to go to the moon and go live there for a few months, or move to Mars and build a house on Mars. We want that so that they have the ability, the option to decide on a whim to go and do that. So that's what I want for my kid. I don't want him to necessarily go into nuclear propulsion, but I want him to have that type of options and future.
Thanks very much for sharing that story.
Thank you for your time.
The Interplanetary podcast is alive!
What did you think of that?
It was very enlightening.
Nuclear everything is going to be insanely important with
Nuclear
space.
Bombs.
Well, hopefully not. Well, unless they're using the bombs.
For bombs for that type of propulsion.
The Orion style.
The Orion style propulsion. Or
Okay,
Daedalus.
Or yeah. So, George, do you know if people have enjoyed the podcast, where they can go? What the website is?
If they've enjoyed the podcast.
If they've enjoyed the podcast. Well, I suppose if they're here at this point, they must have enjoyed it slightly, because
they may have left it
must
on.
be about an hour and a half in now.
But just left it on. Forgot that they,
fell asleep.
Fell asleep. That's the only people that will be this far in.
Wake up, wake up. So if you've woken up and thought, well, I've listened to it now, can I go to the website? You can go to www.interplanetary.org.uk. And if you're really, really, really interested in pushing it further,
Patreon.
You can join us on Patreon. It's pretty good. And you can find that at www.patreon.com/interplanetary.
.org.
No, just Interplanetary.
Just Interplanetary.
Yeah, just Interplanetary.
Where the Force actually-
Yeah, because we've done the Patreon.com bit.
We've done the
So you can go straight there. Of course, you can get to that via anything. If you go to the Interplanetary Twitter, you'll find our link tree there, so you can get to most things from that. Anyway, it's been an absolute thank you, George, for literally stepping up at the last minute so that we can get this podcast out on time. You're a legend.
So it's good. Any time, Dad.
Oh, that's good. Now, what are you up to at the moment, George?
I'm working on some short films, CGI short films. Working on my chess skills. Trying to get to Grandmaster.
And you've managed to combine both.
I have actually. I mean, I finished that short film, but I'm now working on another short film based on the Isaac Asimov short story, The Last Question.
Oh, The Last Question. Now, that is a good sci-fi story.
It's a sequel to The First Question.
There's one book in between called The Middle Question.
A question asked the same amount of times after the first than it was the last.
Yeah.
I think it's the full title.
Is that right?
Yeah.
Okay. I do remember in my listening because I had it on Audible, a bunch of Asimov stories, and that one does stand out as one of the
agrees.
very
He said,
best.
Out of all the stories he's written, this is by far the best one I've written.
Really, because it does stand out when you listen to it. So yeah, well, I'm looking forward to it. And if anyone wants to check George's work out, what's your YouTube channel?
If you look up George Russell Media on YouTube and just go search filter by channels, I think it will turn up just anyway. And then
I'll stick a link on the.
Stick a link. Yeah,
I'll stick a link.
It's the future,
But
Dad. It's 2008.
Yeah, and of course we've done you've done a few spaceship renders and stuff like that. Haven't you?
Yeah.
It's not as many as I'd like, but there we go.
Well, you've got to commission them.
Yes, no, that's true. I've been a bit naughty. Right, okay, that's it. Well, I hope you enjoy the rest of your week, Spodcats. I'm going to say goodbye. Bye, bye, Spodcats!